All right, in this video we're going to do the couple pages here about absolute and conditional convergence. Now this isn't ideal because there's some questions here that usually in class I would pose to you. So I'm going to have a couple of times, I'm going to ask you to pause the video, kind of think about the question. I think it's better for your brain to pause and think about it instead of me just kind of spewing off some facts for you. So first let's kind of work through this here. We've talked about, we know that when an alternating series converges, if it's not alternating, it might not converge. And we have a series that we've studied a lot that illustrates this. When it doesn't converge unless it alternates. As an alternating series, it converges. When it's non-alternating, it doesn't. Can you think about what series that was? I'm actually going to pull the notes up here from the previous page. That is the alternating harmonic series. As an alternating harmonic series, it converges, but the harmonic series itself does not. It's the harmonic. This one diverges, but the alternating converges. So here's the question. I'm going to ask you to pause after we read this. What if we took the absolute value, and what if it converged with all positive terms? What do you think that would tell us about letting it converge without the absolute value? So say there's some negative terms in there. What if it converged if we made them all positive? What do you think that would mean and why? So why don't you pause the video and think about that. All right, I'm not actually going to leave a long pause in the actual video because you were supposed to pause it. Did you pause it? Hopefully. All right, so let's talk about this. The key here is that if we can take the absolute value and all the terms are positive then, and it converges, well, letting some terms be negative once in a while is certainly not going to hurt it. That's just going to shift it closer to the actual sum. So this also converges. So this is a theorem about, it's called the absolute convergence theorem, and it helps us deal with series that have negative terms in them. It says if you take the absolute value of all the terms and then find the sum, then if that series converges, then the series without the absolute value also converges. The proof of this is pretty short. You should be able to follow along. There's some kind of leaps in here that like, well, I wouldn't have thought of doing that, but that's okay. That's not the point of the proof. So what we're going to do here is we are going to try to use the fact that the absolute value converges and try to get a comparison with it maybe having some negative terms in it. So here's what we're going to do. Since the absolute value of a sub n is either it's a sub n if they're already positive, or the opposite of a sub n if they're negative terms, a sub n plus the absolute value of a sub n, well, it's either 0 or double the absolute value. So we're going to say that's between 0 and double the absolute value. Right? If it's already positive, then it's just double that. If it's negative, then adding them together will actually be 0. Now we're going to assume this, right? We're going to assume this and try to show this. So we're going to assume the absolute value series converges. So if the absolute value converges, then certainly putting that 2 in there also converges. Right? I mean, that's pretty clear. We're just doubling each term. So that's not going to change whether or not it converges. And in here, I have a comparison. Since a sub n plus the absolute value of a sub n is less than or equal to double the absolute value of a sub n, the series a sub n plus the absolute value of a sub n must also converge. Think about what the reasoning would be there. By the direct comparison test. Okay, so we have this one converges, and we know the original series, the sum of the absolute values converges. So now here's what we're going to do. We're going to make up a series that you wouldn't think of doing by yourself, but we're going to say, you know what? If I subtract these two series, that will give me my original a sub n series. Right? So here I have a sub n plus the absolute value, but I'm subtracting the series with the absolute value ones in there, so all I'm going to be left with is a sub n. But this one converges. We just said that. This one converges. So I'm subtracting two convergent series. This one has to also converge. So let me write that here, but the a sub n plus the absolute value of a sub n series converges. And the absolute value series by itself does as well. So our series without the absolute value also converges. I can give you a fun symbol here as well. We have the three dots as our therefore. Well, we can do a box. That's the end of proof. End of proof. So there's some definitions that kind of come from this. We have different types of convergence now. We have a stronger convergence that if we take the absolute value and that converges, we call that absolute convergence. So a series is absolutely convergent if the sum with all positive terms converges, because that one implies it'll converge even without the absolute value. It's conditionally convergent if the series converges. Maybe it's an alternating series like the alternating harmonic, but if I take the absolute value, that one diverges. So this one, an example here would be the alternating harmonic. So an example here would be the alternating harmonic. If I take the absolute value of that, then the negative 1 to the power of n plus 1 doesn't, it's not negative or positive, it's just always positive 1, and that diverges. So that's an example of a conditionally convergent series. So we have one additional layer then when we test for convergence. If we find out it's convergent, we need to specify if it has negative terms. Is it convergent because of the alternating part, or would it converge even without that? So let's do a couple of examples here. Look at this crazy one here, this negative 1 to the n squared plus n over 2. So check this out here. If n is 0, then it's 0 over 2. Negative 1 to the 0 is 1. 1 over 3 to the 0, that's 1. If n is 1, we've got over 3 here. 1 squared is 1 plus 1 is 2. 2 over 2 is 1. So that's a minus, a negative 1. When n is 2, it's going to be over 9. 2 squared is 4 plus 2 is 6. Divided by 2 is 3. So still negative. That's weird, right? It went positive, negative, negative. When n is 4, 4 squared 16. Wait, no, we were at 0, 1, 2, 3. When n is 3, 3 squared is 9 plus 3 is 12. 12 over 2 is 6. Negative 1 to the 6th will be positive. 1 over 3 cubed is 27, etc. So this is not an alternating series. It has some positive and some negative terms, but it does not go plus, minus, plus, minus. So here's the thing. Let's look at the sum. N goes from 0 to infinity of the absolute value of negative 1 to the n squared plus n all over 2, all over 3 to the n. Well, that's just the sum. N goes from 0 to infinity of 1 over 3 to the n. All of that crazy stuff when I take the absolute value is just all 1. It doesn't matter if it's negative or positive, it's just 1. But this is a geometric. All right, we've done this one before. 1/3 to the n. Converges. It's geometric with r equal to 1/3, which is less than 1. So what we would conclude is, therefore, the original series, n goes from 0 to infinity, negative 1 to the n squared plus n over 2 all over 3n, converges, and we're just going to add here converges absolutely. So we just added that additional word there that it converged absolutely. All right, the next one, a little bit trickier there. This is an alternating series. Might give you some hints there. Guess I didn't really need those brackets there, did I? All right, if we take the absolute value of that, we get the sum and goes from 1 to infinity of just 1 over the square root of n times the natural log of n plus 1. So I think we did one kind of similar to this with the square root of n times the natural log, and we know the natural log grows very slowly. If you recall, we ended up comparing it with 1 over n, but that comparison's a little tricky. So square root of n and the natural log of n plus 1. This is actually, the square root of n is greater than or equal to that for all of our n's, for n greater than or equal to 1. The natural log of 2 is less than 1. The natural log of e is 1. And then the natural log grows slower after that. So this is true. If we multiply both sides by the square root of n, that's definitely true. And so we get n is greater than or equal to the square root of n times the natural log of n plus 1. And if we take the reciprocal, 1 over n is then less than or equal to 1 over the square root of n times the natural log of n plus 1. So we have our series that we want above a divergent series. Since, let's squeeze it in over here, since, I should have done this over there, since the series 1 over n diverges, it's the harmonic. Our series 1 over the square root of n times the natural log of n plus 1 also diverges by the direct comparison test. Now here's the thing. There's more space. Because, do you know why? All this means is that when I take the absolute value, it didn't converge. But there's still another test I can use. I can still use the alternating series test because it still is an alternating series. So right now I've shown, oh shoot, it's not absolutely convergent, but it might be conditionally convergent where it diverges with the absolute value but converges with the alternating series. So now this is basically all worthless. Well, I mean, it's not worthless. It's not absolutely convergent. So now we need to check alternating series. So let's write it as an alternating series. I'm going to write this negative 1 to the n times 1 over the square root of n times the natural log of n plus 1. If you recall, there were two conditions. First one is that the limit as n goes to infinity of the non-alternating portion here, it has to be 0, and that's clearly true. And a sub n plus 1, which would be 1 over the square root of n plus 1 times the natural log of really n plus 2, that has to be less than a sub n. And that's easier here because it's all in the denominator. And so that's definitely less than these, natural log of n plus 1, which is a sub n. So these are both true. Those are our two conditions. So here's the wording. We're going to say, therefore, the series n goes from 1 to infinity, negative 1 to the n over the square root of n times the natural log of n plus 1 converges, but converges conditionally. So really with an alternating series, you need to specify, and it converges conditionally by, whoa, I haven't wrote that, by the alternating series test. So when you get an alternating series, you have to specify, did it converge absolutely? Does it converge if all the terms are positive, or does it only converge because of the alternating series test? And so in this case, this one only converged because of the alternating series test. All right, so that is it for that video. And I think we'll hold off on the last page in the notes for a different time.